of the perovskite with the electric constant of 25. This is normally called the geometric capacitance. But when you go to lower frequency, you have another very big polarization. It's quite high. This is universally observed, but sometimes it can be suppressed, especially for organic contacts. And this is now attributed to surface contact phenomena related to the ionic double layer. So this is our work with Huson Kim and Angyu Park 2015, where we have correlated the extent of hysteresis with the size of capacitance. So there's and this is well known in many solar cells, even the di-solar cell and others, that if you have big capacitance, you have more or less current in forward or backward, and you have hysteresis. When you suppress the capacitance with an organic contact, then you have less hysteresis. Okay. So this is the typical hysteresis, but there is another hysteresis that goes the other way around, in which the forward current is less than the reverse current, and this is called inverted hysteresis, observed many years ago already. And the inverted hysteresis, we show that is related with an additional feature of the impedance, because we have not only RC arcs, we have also this feature that is associated to induction. And this is observed in many different samples of perovskites. So it's very typical also, and it's very important for the very low frequency features of the perovskite. Okay, so I will explain now a new phenomenon, new in the name, because we have given the name to it, but it's observed across many different fields. And it is the interpretation of the inductor that I just commented. This inductor, what is this? So the people have speculated for many years the origin of the negative capacitance associated to this, and now I have a different name, which is because this is normally associated to an inductor, but it's a special inductor because this is the electromagnetic inductor that you learn in the textbook of physics, and this is created by electromagnetic induction. And then you have two main properties. You have an impedance proportional to the frequency, and you have a voltage proportional to the derivative of the current. So a change in current creates a voltage and electromotive force. Okay, so this is the normal induction. But you can also observe the inductive response, the same inductive response, in systems that don't have any magnetic field variation or electromagnetic induction. And this we have called it in a recent JAX paper, the chemical inductor. So now, the chemical inductor is not related, as I said, to inductor. We call it chemical because in opposition to the physical electromagnetic induction, and it's formed by the coupling of two different equations. There is one conduction equation and one relaxation equation. Okay, so we have the two main variables of a conducting system, the current, the voltage. We have a capacitive current, and here we have the conduction current. But the conduction current depends not only on the external voltage, but also on an internal parameter X that can have many different interpretations, and this is universally valid because this structure is very common. Then the X is not instantaneous. It responds with a relaxation time tau k. And if you have this structure with a memory effect, then this is what I call the chemical inductor, and there are many different interpretations to the X then, okay? But whatever the interpretation, if I have these two equations and calculate the small perturbation, then I will arrive to this equation in which current is proportional to voltage. This is an impedance. The impedance has the form of this function and can be pictured as an equivalent circuit. So here I show you that whatever the meaning of the slope variable X, it's going to give an inductive response. That's why we call this general mechanism a chemical inductor. So here I explain you better the physical interpretation, because we have a conduction polarization system by these two equations that I just mentioned. So we consider first the very short time response. In the short time response, the X don't play any role. So you have two currents. You have a conduction current by the F function here, and you have a polarization current due to the capacitance. This is the initial response. But when the time becomes longer, then you activate the X. So you have more current. And the capacitive current disappears. So as you're having more current, you are going to have less resistance. The resistance is going to decrease because you have another parallel pathway. Okay, and this is the meaning of the inductor is that with longer time, your current is going to increase. We can see it also in the frequency domain by using the equivalent circuit. High frequency corresponds to short time, and then at high frequency, the inductor blocks the passage of current here because the inductor impedance is proportional to frequency, so that we have only RC, and the RC is an arc in the impedance plane. Okay, but when we go to low frequency, then the inductor acts and introduces a new resistance here in parallel, so that, as I said, the total resistance is decreasing, and this inductive action goes into the fourth quadrant, is associated with the negative capacitance. So there are many examples of this construction that I call the chemical inductor. Here is our paper on negative capacitance of solar cells on 2006, where we measured many different technologies that show this effect, this inductive arc. And you can see that the circuit that we proposed was with the RL the same that I'm saying now. Here are examples from organic LIDs, from thin film solar cells inorganic, from highlight perovskite. You can see this has a very big inductor or two. So this is very common in perovskites, as I said before. In electrochemistry, this is a very familiar construction. It has been known since the 1980s. And you have a big inductor in electrocatalysis or corrosion, and you have even negative resistance, which is an additional feature, and you can generate oscillations in electrochemical systems. These are examples of anodic dissolution of copper, of dissolution of manganese. So you have always this very big inductor, because in corrosion or in electrocatalytic reactions, you have an intermediate step of reaction, and this creates the induction effect. Also, lithium atom ion batteries, in membrane proton exchange membrane fuel cells, you have these slow reaction effects also with very big inductors. And historically, the first occurrence of this phenomena is in neuron models. This is the Hodgkin-Huxley model for biological neurons. This is an extraordinary model that describes very well the response of the neuron to the action potential, and is used for characterization, experiments, for creating neuromorphic computation. So the Hodgkin-Huxley model of 1950 has this conduction equation, and then has three slow variables. So you can have many depending on the complexity of the system, but the structure is exactly the same I showed you before: the capacitive current and then the conduction terms with the three different variables N, M, H. We have calculated the impedance of the Hodgkin-Huxley model, and of course you have the inductor. And in fact, the inductor was observed by Kenneth Cole in 1940, much before than the publication of the neuron model. It was measured directly in big squid neurons by Cole, and he showed this inductor, but of course they couldn't interpret it because they were looking for interpretation in terms of coil or some physical effect. And now then the Hodgkin-Huxley model clarifies that this is just because of an ionic response of the ion channel. Okay. This is a simpler ion model, neuron model called the Fishhorn-Nagumo model. This is made only with two equations, one conduction equation and one memory effect, but describes also very well many properties of the neurons. And I have this is a very good model to understand the inductor that is inherent in the neuron models, and also the oscillations. The oscillations require another property, which is the negative capacitance. As I said before, you can see here that when the system becomes unstable and oscillating, like in neuron spiking, we not only have the inductor, but we have also, and the capacitor, we have also a negative resistance. Okay, so this is now established then that we have a general feature called the chemical inductor, and now we have characterized it in the frequency domain, but how does it go into the time domain, which is the initial question about hysteresis that I commented before. Now we want to make the connection of the frequency domain response and the time domain response. So then I clarify this is normal hysteresis. It's called like that. It's like clockwise here, counterclockwise here, and this is the inverted hysteresis, in which, as I said, the forward current is larger than the reverse current. And you can pass from one to the other very simply by just modifying a little bit the contact of the perovskite solar cell. This was shown in this paper, and so it's very much related to ions arriving at the interface. Now this is very well established. So let me remember a little bit what is the JV curve measurement. It's making steps of voltage with time, and then the system at each moment has to relax. So if you give enough time to each step, the system will arrive to its equilibrium state. But if you do it fast, it's not going to be possible for the system to relax to the final equilibrium state. So going forward will be different than going in reverse. Forward, reverse. And then we will have the hysteresis, which is related only to capacitive charging. So this is capacitive hysteresis because in capacitance you have a transient current, and the transient current is proportional to the scan rate, so that when you make faster transient, you have more current. This is the typical square shape of the capacitor. Okay, so you to the basic JV curve, you add capacitive current, and then you have more current when you go forward. This is very well established, all the properties of capacitive currents in the year 15, 16. This was clarified very well by Germán García Belmonte. But we have another phenomenon, which is the inductor. And the inductor corresponds to a negative capacitance if we calculate the total capacitance. So it goes the other way around. When you go faster, the current is more negative, so it's decreasing. So now it's going all the other way around. So we have to explain the two types of hysteresis. And here is the typical inverted hysteresis when you will be dominated by the inductive, so that we can make this summary of concepts. We can have capacitive hysteresis with normal capacitive response with normal hysteresis, but if at very low frequency you are dominated by an inductive impedance, then it's going to be the other way around, and we call it inverted hysteresis. So we have now made a lot of studies in which there is a very good correlation of the actually measured impedance spectroscopy properties and the hysteresis properties. Okay, so again, I show the previous slide in which we connect normal hysteresis with capacitance. And here is a work by Francisco Fabregat Santiago in which they correlate the inverted hysteresis with the appearance of inductive effects at very low frequency. So we have the two things, and I want to give an interpretation of the chemical inductor in array perovskite. So what does it mean? What is this inductor? So it's related to the ionic effect, and many authors like Vaughan-Tres or Jacobs or Piers Barnes and David Moya, many authors have remarked this, that there is a coupling between ionic and electronic dynamics is the essential origin of this hysteresis effect. So when we make the initial voltage, then we have electronic current and polarization capacitive current. And we have some ion motion, but the ions have not arrived to the interface. They don't contribute to the current. At longer times, they do get to the interface and they create additional recombination. So this is more current, and this is the characteristic of the inverted hysteresis of the inductor, that the total resistance is decreasing over time, and this is not good for solar cells because it means that you have more recombination. So we have made different models over time, like this surface polarization model, and the mechanism is the same. There's something slowing down response of ions at the interface, and this is controlling recombination. This was the first model providing the inductor effect, and so I think we have a very good explanation of the inverted and normal hysteresis in terms of the impedance properties, capacitive or inductive. So here I show something which is very nice, more complex, related to this topic, because now if we analyze bromide perovskite solar cells and other types of perovskite solar cells with voltage, there is a change of pattern. You measure the impedance at different voltage, so up to 1.2 volts, because this is a wide bandgap solar cell, so that you have to go to 1.2 to make a transition. But before this transition, we have two arcs, and it's totally capacitive. But when you get to 1.2, you see that here it becomes unstable, developing something, and suddenly you see that is a very big inductor at low frequency. So this slow dynamics of recombination control by ions is onset at this voltage, 1.2. So this means that at low voltages we have one type of hysteresis, normal, and at high voltage we must have the other type of hysteresis, which is inverted. And this is exactly what happens. You see the big hysteresis feature. This is in the dark. So now we see a counterclockwise hysteresis, typical of these bromide cells. But when we plot it in logarithmic scale, we can see that at lower voltage, invisible here, there is a region of capacitive hysteresis in which the current is higher for larger scan rate. So this is capacitive and this is inductive, less current at higher scan rate. So this is a transition at some point between capacitor and inductor, which is extremely interesting. And we have formulated a general model using the chemical inductor and different voltages to explain this feature. And we think this is a very good tool making these models. This is now a nonlinear model, but it can go into different realization. You can explain different things. You can explain cyclic voltammetry, and you can explain impedance spectroscopy if you take the linearized version and calculate impedance spectroscopy. So in the end, we want to have a model of the type of the neuron models of Hodgkin and Huxley that explain very complex systems with just a few differential equations that are highly nonlinear. Okay, so yes, if I calculate the impedance associated to this model, I obtain this general equivalence circuit, and I can have the capacitive domain, a transition domain with capacitor and inductor, and a pure inductor domain when the capacitor disappears. So we can track all the parameters in the model and find an explanation of the time constants. And here is a very important property in which the capacitive and inductive time constant are continuous over the transition. So I repeat, now we having this type of quantitative models with a few differential equations, we can explain the large signal time domain and the small signal frequency domain. So this is a very powerful resource, and we want to exploit it for different types of systems. One thing we can do is calculate all the transients now that we have a good model, and this is for a voltage pulse, and it has been observed since the beginning of research on perovskite that the switching on of perovskite by a light pulse has a negative spike. So first the photocurrent goes down and then it goes up. Okay, and this was very difficult to explain with recombination models. And in fact, as I said before, here we have to consider the coupling of recombination and ionic effects, because you can see that we can have an initial capacitive discharge, okay, that would come here, but as time goes on, we have an additional recombination, okay, so that the current is higher, so that now the inductor sets in and introduces this additional effect, so that this model of the chemical inductor of nonlinear differential equations in the neuron style can explain very well this transient and other phenomena. We are also now dealing with memory effects and things like that. Okay. I will change the topic now from the memory effects to the measurement of different types of frequency response techniques. And I am going to recall measurements of 15 years ago on solar cells and other systems in which we could make some electron diffusion models for transport, like these transmission line models that became very popular. And this was very successful to explain diffusion in these systems. So that we could characterize very well electron transport in dicity solar cells. But in the high-light perovskite, this did not happen. We could not observe diffusion with impedance spectroscopy because the diffusion coefficient is much higher. But anyway, we see two arcs, as I mentioned before, but we don't see these lines of 45 degrees that are the standard manifestation of diffusion. So we have been using other methods because, of course, as I commented before, we have the JV curve, but we can stimulate the perovskite solar cell also with light. And then if I stimulate with light and measure the current, this is the external quantum efficiency that is complementary to the current voltage curve. This is also a very important characteristic of the solar cell using light stimulation. And we can make the corresponding frequency techniques. We can stimulate with modulated light and measure modulated current. This is called intensity modulated photocurrent spectroscopy, IMPs, and the transfer function is Q. And we can measure also stimulate with modulated light and measure stimulated voltage, and this is IMBs, and the transfer function is called W. So IMPs is a very important classical technique of photoelectrochemistry. Our work on perovskite solar cell was done by Sandeep Ravishankar. He's now with Thomas Kirchhardt in Munich. And he did many, very nice characterization works that are highly pioneering because he could apply our method of equivalent circuits to the perovskite solar cells. So this is a review article when you can get updated about that. And today I want to consider another effect which we discovered recently, which is analyzing diffusion with IMPs. And this analysis comes from the normal diffusion equation that was developed by the master Professor Laurie Peter. And we have revisited it, and we find that when you eliminate on one side and measure the photocurrent at the other contact, you have features that are negative. The real part of the Q transfer function of IMPs becomes negative. Okay, but the at low frequency it's totally real. There is no negative low frequency feature, but at high frequency it becomes negative. Okay, and this was observed. But you see that it was sometimes suppressed, even by us, because this you can see that this spectrum is going to be negative, but it has not been measured or it has been cut somehow, so it was not reported. So now we really could make this very reproducibly, and in combination with the group of Felix Dessler, we could use this part for fitting and they calculate electron transport coefficient, and it's a new method which is very successful. But also we can do the transients, etc. But now what we can do, having different techniques, is to use them all at the same time. And this is what I call correlative frequency techniques in solar fuel systems. So this approach was developed with Luca Bertolucci in his PhD work, and he discovered this general nice formula, because in each technique you use a different equivalent circuit, but they are all the same with different connections, so that the different transfer functions are not independent, and then you have the connection between the three, and this must be realized by the experiments. Okay, so now here I show you very nice data of IMPs. These data were obtained by Agustin Bow and Adam Pocket. And now I have to warn you that this high frequency data sometimes is very problematic, because you can have artifacts and the setup can interfere with the high frequency measurements in perovskite solar cells. But this is very safe, because you can see data also from Adam Pocket, in which time and frequency domain was giving correlated characteristics. So these measurements are very reliable. It's a very large negative part. As I said before, we did suppress this part because we didn't understand at the time of publication, but it's giving a negative part, and this part contains information now about the diffusion coefficient of the perovskite solar cell, while the impedance spectroscopy doesn't have it. So it's very interesting that now we can observe electron diffusion both in IMPs and in IMBs. You can see the negative part on both. But when you make the division of the two, we don't find a diffusion impedance in the impedance spectroscopy. So that we are concluding that they don't contain the same information. And the reason is that the measurement is not really the same, because, as I said, you can observe this negative part when you make very short distribution of electrons by strong absorption, and then you make them cross the samples, and this doesn't happen in impedance spectroscopy because it's just an electrical characteristic. So this is a new insight, and then it has developed now for photoelectrochemistry with bismuth vanadate water splitting, and this has been done by Fran Fabregat and Agustin Alvarez. So they run the different types of measurements, and we can correlate the different spectra using the central formula of Luca, and you can see here the different spectra. You can see the IMPs going negative and also the IMBs. It means that you are detecting the diffusion coefficient of electrons in the photoelectrodes, and then you can feed all the three techniques at the same time and obtain a highly reliable diffusion coefficient of electron in bismuth vanillate. I'm going to finish my talk with a new method related to the ones I am mentioning, because let me recall that I was giving here a catalog of possibilities. This is light coming and current or voltage going out, but there is one more thing that one can do, because in light emission systems like perovskite or LIDs, one can see the light outgoing due to radiative recombination. So one can have put a voltage and observe the radiance in addition to the current voltage curve. So if we stimulate with light and measure the voltage, this I called before IMBs, and the transfer function is W. Now, this is an inverted IMBs, will be to stimulate with the voltage and measure the outgoing current. So now there is an additional degree of freedom. There are not three, there are four, and we have worked out this possibility, and this was published in Advanced Materials last week. It's a new thing in which we have now included the part of the equivalent circuit that is creating radiative recombination, which in impedance is very small. And in fact, this is the theory. So you can see that we have the impedance spectroscopy always the same, because this is the current voltage characteristic. But depending on the radiative time constants, there is a very big change of possible spectra. And this has been detected by Rafa Sanchez. And you can see that we have this spiraling spectra, and the spiraling spectra is going to give us information about this part of the equivalent circuit that is the recombination, separated from the low frequency typical memory effect, which is this part that you have in impedance spectroscopy. So you have this slow phenomena occur also in the light modulated technique, but you have other arcs that are not visible in the impedance because it is impossible if you don't detect the light. So I think this will be a new method, also useful to address from another point of view, the memory effect or accumulation, or about these repetition pulses that Ivan Shevlin was talking before. So I think this will be a very important development. I had also some slides on neuromorphic computation using the neuron model and how to reproduce it, because it is interesting that with high-level perovskites we can make memristors. Memristors have this big memory effect with the equation, which is the same as the chemical inductor I said before. And with high-level perovskite we can make memristors, and the memristor you can see now that is a system that has a very big inverted hysteresis, so that with this you can do two conduction state, less conduction or more conduction, are related to the this big hysteresis. We can obtain different impedance characteristics, and of course, when we have the big hysteresis loop of inverted hysteresis, we have the big inductive response, and this has been shown by Antonio Guerrero and Cedric Gonzalez for the perovskite memristor. So these equations I was telling before, that we can use one or two or more internal degrees of freedom to make neuron style equations, are very useful now to address memristors, because they have very pronounced dynamic effects, and we have done this, and we think this is very successful for describing high-level perovskite memristors. So I will stop here and thank my colleagues, because I think I gave a lot of material already, and I would like to thank you again for the invitation and expect the questions.
Yeah, thank you, Professor Yuan, for your wonderful talk. Now the floor is open for a few questions. Uh, Professor Biskra, this is Satya here. So I was a little intrigued by this comparison between the capacitive and the inductive thing. So both of these, according to you, comes from the ionic component of the charge transport, is it?
Uh, okay, it's not only transport, it's that the ions are going to affect recombination because I think the dominant current in the perovskite solar cell is electronic. The transport, I don't think is very significant. But the transport change the polarization and conduction. So yes, these slow effects may be very much associated to electrical effects caused by the transport, by the ion, sorry, but not necessarily only ion transport. Mhm.
Do you lost connection or?
I lost the connection with the conference.
Yeah, I mean, I also don't see. I just see you.
Yeah, me too, me
Well,
too.
yeah. Very nice talk, by the way. I mean, I'm trying to understand these techniques what you are using. It's I never used it before, but it's really like um, it's of course interpretation is a problem. But I mean, you see signals, but I mean, you seem to be able to interpret it, but it's not for like an average person. You know, you need to somehow
No,
use